All right, so in this video, we're going to be deriving the matrix vector equation for multilinear regression, starting from the basic principle of why the approximation error should be perpendicular to the basis vectors. So if you start off with a desired vector v and a basis vector of u, you can add a coefficient onto the basis vector u that will extend your basis vector to the point where your error vector is perpendicular to your basis vector. So that will give you the equation of your desired vector is equal to your coefficient times your basis vector plus your error. And so rearranging this equation, you can get error is equal to your desired vector minus your basis vector. And so another equation that we can derive from this is that your basis vector times your error is equal to 0. The dot product of your basis vector and your error is 0. And so when you plug in your error into your dot product of your basis vector and your error, you can minimize your error. So we're going to plug in. So your basis vector minus your coefficient times, your desired vector minus your coefficient times your basis vector, dot product with, that's a u. Your basis vector is equal to 0. So multiplying that through, you will get your desired vector dot product with your basis vector minus your coefficient times your basis vector dot product with your basis vector is equal to 0. So now isolating for your coefficient, you're going to get C1 times U1 times U1, dot product with U1 is equal to V times U1. Yes. And then so you can isolate for your coefficient, leaving you with C1 equals your desired vector minus your basis vector, dot product with your basis vector over the dot product between your basis vector and your basis vector. And so this is going to be our matrix vector equation for multilinear regression. So for this portion of the video, we're going to be fitting the given water vapor pressure data using multilinear regression by transforming the Antoine equation to linear form. So starting off with the Antoine equation, we have log P equals A minus B over T plus C. So transforming this into the linear form, we have to multiply everything by T plus C first. So we'll have T plus C times log P equals t plus c times a minus b. So expanding this out, we will get, t log p plus c log p equals at plus ac minus b. And so isolating for our two known values, which is temperature and pressure, from our water vapor pressure data, we will get t log p equals at plus, sorry, I'm just going to organize it like this. At minus c log p plus ac minus b. And so kind of writing this as a vector statement, we will have a vector of t's we'll have a vector of negative log p's, sorry, p1, p2, and then a column of just ones. And so this signifies, sorry, first we have to multiply by our unknowns. We're going to have a, c, and then d. So this part right here is what's going to be our d. So d equals, sorry, I keep hitting my mic with my pen. D equals ac minus b, and then this can be arranged to b equals ac minus d. So that'll be our d in this equation here. So this portion here is going to be, whenever you multiply it out, it's going to be our at from our above equation. And then this is going to be our negative c log p. And then this will be our d. And so once again, our d is ac minus b from our equation. And then this is equal to a vector of t log p. All right. So now, since from part A, we determined that the error should be perpendicular or orthogonal to the basis vector, we should multiply both sides by the transpose of A. So by AT, in order to get a 3x3 set of equations multiplying by our set of three unknowns. Okay, so the first thing we're going to do in collaboratory is import the data. So we're going to use wget. And then go ahead and grab the link. All right, so now Collaboratory has grabbed the data from this GitHub link. So next we're going to, import numpy. So next we are going to analyze the data. So in order to do this, we want to load the text. Sorry. Then we're gonna have to set this equal to something. So data equals our load text, and our delimiter is going to be commas. Okay. And I almost forgot. We have to set our temperature and pressure equal to the transpose of the data. Because instead of having columns of temperature and pressure, we want to transmit that to rows of temperature and pressure. All right, so next we are going to establish the design matrix and the unknowns. Okay, so V is going to be our design vector. So it's going to be so that this is where our equation comes in. So the first one is going to be T. Next one is going to be, sorry, keep forgetting the NP. Okay, NP log P from here. And then our last one is going to be our column of ones. So we're going to have our column of ones there. All right, now we're going to establish our unknowns. So A, C, and D are equal to our linear regression model is going to be the transpose of our vector V established above. And then in this coding language, at is the dot product symbol. So we're going to do the transpose times itself. And then we're going to do transpose of V. Sorry. With the dot product of our vector on the other side. So that's going to be our T log P. So it'll be T times NP dot log of P. Okay, I almost forgot. B equals, what was that equation? It's going to be B equals AC minus D. Okay, so next we are going to import Plotly so we can make our plot. So from Plotly dot subplots import make underscore subplots. The next thing we have to do is make the subplots. So plot equals np dot linspace. It's going to be Work? Okay. So fig equals make sub plus oh shoot. Did that? Shoot. All right, so next we're going to add our scatters. So fig add scatter. Our x is going to be our t. Our y is going to be our p. And then our mode is going to be markers. And then we're going to add our second scatter. Fig dot add scatter. Our x is going to be our plot, which is our model for t. Our y is going to be our Antoine equation, which is a minus b over plot plus c. And then we're going to update the y-axis to be logarithmic. Oh boy, what did we do wrong? Oh. Work. There it is. Okay. So as you can see, the model for our linear regression for the Antoine equation fits pretty well for our data points. Okay, so now for the final part of this video, we're going to derive the matrix vector equations for multilinear regression through minimization of sum squared error or least squares between model and linear combination of basis vectors. And then we're going to compare the results to part A. Our error equation is going to be our desired vector y minus the summation of ci phi I when summation is going 1 to n. So our sum squared error is going to equal the dot product of this times itself. So it's going to be this guy. So if we write out all of these terms, we're going to end up with we're going to end up with 2 of the summations with the dot product of y. And finally, we're going to have we're going to end up with an embedded summation of sorry, should probably draw it differently. So to split these up, we're going to assign a different value to each of these summations. So the first one is going to be p. The next one's going to be q. So we're going to have the first set of c's be p, and the second set is q. And the same thing for phi. All right, so in order to minimize the sum squared error, we're going to want to take the derivative. So the derivative of the sum squared error with respect to, so we can't take the derivative with respect to p or q, but we want to, I mean, we could, but we want to set a value within these summations where both of them equal one value at one point. So we're just going to set that value equal to j. So to minimize this derivative, we want to set it equal to 0. And so when we do that, when we take the derivative, we get this yi term is going to be 0. And then this next term is going to be -2 phi j times y. And then this final term, we're going to have to take 3 separate cases. We're going to have one case where p is not equal to j and q is not equal to j, which will just have 0. And then we'll have p is equal to j, but q is not equal to j. And in that case, we will have the summation for q is not equal to j. And we will have CQ phi q phi j. And then for the scenario where we have p is not equal to j and q is equal to j, we will have CP phi p phi j. And then in the situation where both p is equal to j and q is equal to j, we will have 2 cj phi j dot product with phi j. Okay, so now what we can do with these two summations here, since there's a gap in both of them at j, and we have a third term over here that has each term at j, we can provide one of the terms at j to each summation to create 2 complete summations. So we will be left with 0 equals -2 phi j y plus the summation of, sorry, there's going to be 2 of these, and they're going to be 2 identical summations. So we're going to have ci phi I dot product with phi j. At this point, you can bring it from 1 to n. So now if we separate these and we have 2 phi j y equals 2 times the summation of I equals 1 to n of ci phi I dot product phi j, divide by 2. Divide by 2, and then we're left with phi j y. Sorry, I need to scroll down. phi jy is equal to summation I equals 1 to n for ci phi j. And so this equation is going to be the equation for all terms. And the equation for one term, we can isolate ci to be equals, I'm going to arrange it like this. We're going to have y times phi j over phi I phi j. So this is the equation for one specific term. And so this is also assuming that both I and j are going from 1 to n. So if we compare it to the equation from our part A, which is, if we scroll up, it's going to be our C1 equals V times U1 over U1 times U1. So if we take that, that is very comparable to the equation we just derived from this method. So at this point, I think we're done. So thank you everyone for watching.